I guess I have the important duty of not letting you sleep because you have to see the last talk, which is afterwards. So, I don't care whether you get something from this, you just have to be awake. That's going to be... Anyway, the talk is called Going Higher, and it's supposed just to be, a game with words, because we have all these things starting with higher in functional programming. We have higher order functions, higher kind of types, higher rank polymorphism, and I just wanted to tell you what all of this is about and why we want this. And of course, this is only because we want to create more powerful abstraction. That's why we are using this higher, because we feel that this empowers us to create better software. Unfortunately, I don't have time to show many examples in depth. So for many cases, I will just tell you we use this for this, but I won't have time to tell you how all of this works together. But just ask me later. I'm allowed to talk even more. Just remember to talk to me before I drink too many beers, just as a general advice. So higher order functions, in the olden days, people told me that they were even, they were happy to have functions because they didn't even have functions because they were, too slow. You had to think, They were only using the assembly language, and then somebody came with this notion of function or procedure, which is just a reusable chunk of code, and you have some input parameters, and you can change the behavior depending on these input parameters, and at the end, if you have the procedure, you just stop doing your procedure, or if you had the function, you return a value. Now, we are used to not only have functions, but even our functions have types. So if we have a function like merge, which takes to key value map, so this map, this is Haskell syntax, and this is essentially telling you merge is a function, takes one map with some type of keys and type of values, key and w, and another map, and it will give you yet another map. So this essentially describes the essence of what this is doing. But what happens if we try to implement this operation? What do we expect if we have these two maps? I'm just making up the syntax. This is not really Haskell syntax, but just you have a map which has in the key 1 a value true, and in the key 2 a value true, and then another map. What do you expect when you merge these maps? And the thing is here, there is no really one answer. You could say, the first one takes precedence, so I want to get the true. Or the second one takes precedence because, this is just an arbitrary choice. You can do whatever. So maybe a possibility would be to introduce yet another argument to say what's this bias. So you would say, I want this to prefer the left or to prefer the right, and depending on this, if I find the same key in the map, I will choose what to do. But why stop here? What if I have numbers and I prefer to take the max of these numbers or the addition of these numbers, or in the case of booleans, I want to take the or the and, because this is not just simple value. This represents something in your domain. So what we really want is a way to parameterize what we are doing, but not by data. We want to parameterize by behavior. We want to control the behavior of this function by some other code which we just tell this function what should you do if you run into this problem. And that's exactly what higher order functions give us. So we can create a new version of merge which takes the two maps plus a function. So that's the first argument there, which takes one value and another value. And this function will only be called if we have two keys with two different values and they conflict. We have to choose one. So we can use this function. And with this, it's amazing because we can implement any other thing I've mentioned. So you can say, I prefer the left thing. So you just pass a function. This is a Haskell syntax for anonymous function. So you take the first argument, you ignore the second argument, and you return the first. Or the other way around, you ignore the first and return the second, or you prefer to use the max function and, well, if you have two numbers, you just get the maximum of both. So that's what we call a higher order function. And I would like to take a moment to explain why we talk about higher order here. So this is because in many conceptual frameworks, ways of thinking, you usually have this division between things of type A and B in such a way that when you have a bunch of A's, you get a B. So you can have a bunch of numbers and put it into a list. Or you can have a bunch of screws and a bunch of metal and put it together, and then you get a car. What higher order says is that there are not really two levels. These two levels are the same thing. So when you get things of this sort, type, kind A, and you compose them together, you get yet another thing of kind A. And this allows you to keep composing all the time, as many times as you want, because you are only working with things of type A over and over again. So for the case of functions, we can speak of these two different kinds of types. So we have ground types. These are the things which really exist in memory. So booleans or integers, list of integers. These are ground types. And in most languages, these ground types are the things which can appear as argument of functions. So we have this division. We have ground types, that's our A's, and then we compose types to get function types. So function declaration, which is a different thing. Now if we speak of higher order functions, then these two things are merged together, which means that we can use functions as argument of other functions, or functions as return value of other functions. So these two worlds have suddenly merged into just one thing, and that's always the same kind of thing with higher order things. We will see two things which were kept separate, and then we are merging them together, and this essentially gives us some new thing to play with. So that's what higher order functions do, and needless to say, higher order functions are everywhere in functional programming. I mean, they are so important that we call our style of programming functional. So everywhere, map, folds, filter, these are all higher order functions. They are really the basis of what we are doing. So I wouldn't really go too much because I guess that by the end of the day, you know what a map is and a fold is. So let me just go on. And I would like to show you an example of how far you can actually get with higher order functions, even though you don't know it. But I mean, it's one of those things you've already know, but you don't know that you know. So that's so this is the folder function. That's the Haskell function which does write folds on a list. So essentially, it gets a list of numbers. For example, you tell it use plus and 0 as function to combine as an identity element, and it creates 1 plus 2 plus 3 plus blah 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 blah. That's the normal fold operation. Like it's usually called fold or reduce in any other language. So that's how the function looks. But the thing is, this idea of fold is not restricted to list. You can write folds for any data types. And I would like to tell you, you should go to the talk which is happening right now also, because that's what it's about. But yeah, you cannot be in two places at the same time, so you're stuck with me. But if you have something like a maybe, where you have nothing or just, you can have a fold which just follows the same structure. It sort of follows the same pattern. You always have this R as return of the higher of the function which you take as arguments, and then every time you have a recursive position, like this tree has subtrees, you get the R replicated there. So I don't want to go into the details of how you build this, but given any data type, you can write this fold, and this is a wonderful thing because people have written actually books about how you can take this idea as far as having like an algebra of how you do programs. But what is even nicer is that if you take this idea to the stream, you can say, I don't need data types at all. You can just say, my list is my function. So it's not like you can get the list and define the function. It's that you just say, my list is really this function. And if you want to, if you trust me into this, you can try to write what the nil and the const, so like the empty list constructor and the element constructor for a list do. Just following the types and you get something like this. And this is called the charge encoding from the data type. And again, it's not my aim that you understand how all of this works. My aim is to just be able to tell you, this is so cool. We don't even need data types. We have higher order functions. They are enough to just recreate anything we have in functional programming. By the way, if you've been in the Lambda core talk, that's sort of the same idea going on here. So if you have a small functional programming language, you can recreate almost every other feature by using a tricky combination of functions. So that's enough for higher order functions. I mean, we all know them, but really you can still keep studying them and finding new things. But let's go to the next. Let's go to higher kind of types. And let me see how much time I have. Okay. So first of all, if I'm talking about higher kind of types, I need to tell you what a kind is. Otherwise, well, what higher kind means is something about kinds, of course. So kinds is what Haskell, or the Haskell term for the type of a type. So because we are so crazy about types, we say, oh, actually, we want to check that our types are correct by using some kinds of types, and we call these kinds. So the idea is that, again, we see this notion of ground type. A ground type is something which exists in memory, and integer is, for example, a ground type. It's something which you can manipulate, can be an argument to a function, and we say that integer has kind a star. Why a star? Don't ask me. Nowadays you can also write type, which is a nicer notation. But if you have something like maybe itself, if I just tell you maybe, or option, or whatever it's called, in itself is not a ground type. It's not something which exists in memory. You have to tell me what kind of thing is going inside of the maybe or inside of the optional. So you can also see that it needs a type argument. So that's why if we ask Haskell what's the kind of maybe, it will tell me it's a star to star, because you give it a ground type, and then the result of maybe applied to a ground type is really a ground type. So maybe of a string is going to have, so yeah, integer has type star, maybe has type star to star, so maybe of integer will have type star. So it's a ground type you have there. So in most languages, and that's something Kotlin people have been talking right before me, is that in most languages you can only abstract over ground types. So if I write my map function and I try to write it in C# or in Java, I can abstract over A and B. I can really write a function which works for any A and B. Or if I'm having an interface or a type class in Haskell, I can speak about things about ground types. So in this case, this is telling me EQ is a type class, sort of an interface, and you implement this type class by giving me an equality function. So it has to take two values of the same type and give you a Boolean. That's essentially what this syntax is saying if you don't know Haskell. But what happened? There are other kinds of commonalities between code. So we have map, which has this type. So it takes a function and then a list of A and gets you a list of B. But if you play a bit, you can write similar functions for maybe and for IO. And we are using this all the time in our code. So we would like to have something which keeps the A's and the B as they are, because we are not changing this too much. What we are changing is the list, the maybe, the IO. So we want to be able to abstract over this line, not over the A's and the B's. And that's essentially what higher kind of types allow us. It allows us to have abstractions which work over this kind of type. So it allows us to abstract, in this case, over the container of the things, not over the things which are contained. So that's quite powerful. And without having this thing, we cannot really write code which is reusable over all of these container types. This is more like an informal thing. It's a design pattern. You say, well, this is like a map. But you cannot write a function like void, which I show here, which works for every map. By the end of the day, if you are using Java or something like this, you end up writing void several times for everything. You still keep the pattern. So when you talk with other people, you might say, oh, it's the void. But then you have to replicate this implementation several times. And of course, this duplication is bad. What we want is to define this function once and for all. And if somebody gives me a new definition of functor, I don't have to write anything else. Void still works here. Again, higher kind of types are everywhere in modern FP. So if you do a bit more of Haskell or Scala, you end up into this cat Scala set. You have names like functors, applicatives, monads, traversables. You don't need to know the specifics of all of this, but all of this refer to higher kind of types. So really, to be able to even talk about them, you need higher kind of types, and that's the extra power you get here. And actually, I have to show you. I will show you my two favorite examples of code in the world. So this is the first one. This type signature is my favorite type signature in the world because it uses two higher kind of types. So applicative and traversable are two different higher kind of types to give you this amazingly generic function, which you can use for any kind of things. And you can just start playing like if I choose F to be a list, and traversable is sort of like a functor in which you can apply an operation on every element, but this operation can have side effects. So what if I choose T to be, I don't know, a maybe, when you get something from A to list of B to maybe A to maybe list of B, which might make sense in your case or not, but by choosing different things, you can just use traverse in so many different ways. So there are so many different things where the solution is use traverse that I really cannot keep count of all of them. But you don't need to stop here. So here again we are using this higher kind of idea to be able to speak of kinds of types with dependent of other types, and they have these higher kinds. But we can even go farther. So being a monad, for example, is a property of a type constructor. So you need to give me some kind of M, which is parameterized by one element. That's why we have star to star. But then you have these monad transformers, which take one monad and generate another monad. So that's, that they have this kind signature there. So it's really one level higher even. So that's like 2 levels up. You take a higher kind of type and you create a new higher kind of types. And if you've seen Michael talk, you know that this work opens a world of possibilities and something similar to Pandora's box for some kind of monads. So again, I don't want to say too much, but the important thing is if we don't have higher kind of types, we are not even able to write this thing because this depends on T having this higher kind of, this higher kind. Something which I also find quite cool going with the theme of folds is that if you have higher kind of types, you don't even have to write different folds. You can just write one fold for every data type you have. And the details are a bit complicated, but it involves separating the shape of your data type. So that's what we define with what it's called a pattern functor. So that's like this list F is like how the constructors of a list look. So you can either have the constructor which looks like nil or constructor which looks like cons. But what is missing is that the parameter of cons does not mention list itself. It only mentions one extra R there. And then you separate the part which tells you the shape from the fix, which is the part which ties the recursion. So it's like you are separating the recursion structure from the shape of the data type. And you only have to write this fixed data type once and for all. And by using this, you can write this generic fold. So this fold works for every kind of data type which is expressed in this fashion. So with this, people just went crazy. Like, you can write programs which manipulate any kind of data type. and you don't even have to you don't have to do any kind of reflection or anything. You can just write this thing. But yeah, unfortunately, as far as I know, there are only 2 languages. The mainstream languages, mainstream with quotes, of course, which support this kind of abstraction. There's Haskell or derivatives such as PureScript or Scala. Rust and Swift, as far as I know, are thinking of adding them. You can also fake them, and the category people have been very successful in faking it into Kotlin. But unfortunately, this is something which we should start complaining about all the language designers out there. Why don't you have higher kind of types? This is all things from the 80s. They already knew this in the 80s. Why we don't have this on every language out there? Okay, so that's all for higher kind of types. Let's go to the last part, higher rank and impredicative polymorphism. And the names are chosen to scare you, of course, as everything in Haskell. So to explain you what's the A and the B here, so again, what's the thing that are separated we are merging, I have to tell you a bit of theory, so a bit of weird names. So this is coming from this I'm going to tell you. So what's the difference between what is called a type and a scheme? This is coming from something called Hindley-Damans-Milner type inference. That's essentially what a compiler like Haskell do to infer the types. And these are Hindley and Milner are the usual ones, but there is also Damas. This Damas was the PhD student of Milner, so everybody forgets about it. But because I'm a PhD student myself, I feel like I should say, no, we count. So anyway, in Haskell, you have this separation between types and schemes. And that's because in Haskell, even though everything looks like the same thing, you actually are doing 2 different things. Sometimes you are writing expressions, so you are essentially, when I speak of expression, that's something which appears at the right of the equal sign. So you say blah, blah, blah equals some expression. And this thing has a type. And in a type, everything has to be really a type, but you have one thing called type variable. So if I write something like the identity functions, x to x, the compiler will create a new type and will tell that it's something called is of type alpha to alpha, where it doesn't know what alpha is. And just because, to make it even fancier, we like to use Greek letters for type variables. But then you also have declarations. And declaration is when you say these functions equal this other thing. And this whole block is called a declaration. And in a declaration, you don't have a type. You have a type scheme. And the difference is that in a type scheme, you can quantify over variables. You can say this works for all A's, whatever the A is. So when I write identity in this way, and this is different from the thing before because the previous one was an expression, but this one is a declaration, essentially the compiler takes this alpha to alpha and says, oh, this actually works regardless of what alpha I'm using. So I can write this for all in front. And that means that when I use ID, I can use this for numbers, for booleans, for lists, for all of this. That's what we call normal polymorphism. And in Haskell, we can omit the outer for all, but it's really there. So I will try to be very explicit about the for alls. So in essence, the expressions have types, and these types cannot have for alls. For alls can only appear at the top level when we have a declaration. So these 2 words, the types without for alls and the types with for alls, are kept separate. So, you already know more or less what a higher rank type is going to be. We're going to mix these 2 worlds. Just to make this completely clear, if you write ID in Haskell, as a declaration, it will have this type, but when you try to use it in expression, it first creates new variables for the A's. So essentially, it creates new types and tries to figure out what's the value for this alpha. But this is important because if I have something like a list which contains the function ID, at first look, okay, what's the type of ID? well, maybe I can take for all A to A. So why not get this type? Why not be a list of for all A to A, have the final type? That's because, remember, when we use something as an expression, we have to remove the for alls. So we first remove the for alls, so we get something of type alpha to alpha between brackets, and then we add the for all at the end. So we get something of type for all A, list of A to A. So this is an important thing, and this is actually the main idea of why Haskell can infer of all your types, because every time it finds something with a for all, it erases the for alls. Okay, so I hope that was easy until this moment, because now it's going to become hard. So can anybody tell me what's the type of this function? And what should be the type of this function? And I'm assuming you don't have type classes, so you are not allowed to say me something which includes EQ or char or something like this. So it's really, the idea is you have a function, f, and you want to be able to apply this to both char and to and a boolean. Huh? It's any. Yeah, but that's super cheating. Not even cheating. Without any's. Okay, so the first thing many people think is, I can give this type. So I'm sort of, the f has to work for anything. So it has to have something of type A to A or something like this, because that's like I'm not telling what the A should be. So it looks like it should work. And then, well, if it's A to A, then I can apply the function to char, and I can apply the function to bool, and I would get a tuple with char and bool. But the problem is, here we have to understand one thing before. When we as programmers write a for all, what we are saying is that we promise the caller of the function that they can choose the type. So when I write here a for all, when I call the function, I should be able to pass something of type int to int, like +1, because I can always choose what it is. So that's like when you have a map of a function, it's not the map function which chooses the type. You tell, oh, this is the function I want to apply, so that should be the A's and the B's in the map. But that's not what we want here. We cannot do this. If I as a caller choose int, this function won't work. I cannot apply a function from int to a character. So I need something. I need something which swaps this responsibility. I need to be able to say, look, you have to give me a function, and you have to promise me that I am able to call this function as I wish. And in order to do this, we need to have the for alls inside, because now nobody is able to choose anything because there are no for alls in the data type. But the function you give me has to have a for all type, which means that the function has to be polymorphic, so I can choose what I want. And actually, I can give not one but two different types. I can say, oh, you have to give me some kind of identity function, and then I can produce a char or a bool. Or another possibility is that you choose what you return, and then you give me a function in which I choose. That's the second thing. So you choose what to return. You choose the R, but then I will choose what to call. So I choose the A. So this has like some part is their responsibility and some part is for me. And in that case, I will just produce two R's. That's two possibilities. And by the way, something which is very nice from this example is that it shows that if you have this kind of types, you have to say goodbye to type inference. So because you have something and you can give it two types, and these types are completely different and mean completely different things because the responsibilities are different in one case and the other, we cannot give types to this kind of thing. So if you start writing this kind of code in Haskell, you end up having to annotate functions. So you really need to write the ... every time you want to define this kind of functions. But anyway, as I was saying before, Hindley-Milner separates between types and schemes, and only schemes can have for alls. And when we have higher rank types, these two things are merged together. So now every argument to a function cannot only be a function, can be a function which has a for all in the front. And that's what we call a higher rank type. I also mentioned in predicative types, and that's just because of historical reasons, people make a distinction. So higher rank types is about allowing quantifiers as in arguments of functions, so the for all can appear there. But you can also think, oh, I may want to have a list of polymorphic functions, something like a list with the for all inside. And as I said, for historical reason, when we have for alls in other data types which are not functions, we say that this thing is impredicative. Or if you really want to become formal, impredicative actually means that a type variable can be substituted by a type scheme, but I don't want to go that far either. Okay, let me see how much time, because I have a bunch of examples. Oh.
More than 5 minutes.
Huh?
A bit more than 5 minutes.
A bit more. Oh, I can do this, of course. Okay, so of course the question here is, by using Haskell or by using Scala, I've been able to show you examples of why you want higher order function, higher rank, higher kind of types. So I feel that I should tell you why you want this, because that's kind of a weird thing. So I mean, one thing why you want it is why not, of course, but then you lose all this type inference. But people are using this. So for example, in Bartosz' talk, he made this type of natural transformations from F to G. And this is a higher kind of, this is one type with a for all here. So look, you have F, G, but the X is not there. It's just in a for all there. So this is really making quantification. So if you think of a function which uses a natural transformation, this type synonym is expanded and the for all appears there. So everything which works with natural transformation, most of the time needs this higher rank type. So if we want to do really more advanced category theory inside of a language, we end up needing this kind of things. Or just another example from category theory, sorry. If you want to declare what a category is as a Haskell data type, you have to give an identity function and a composition of two arrows. You end up having something like this because the identity has to work for any object, so you need a for all inside the record. So you also end up needing for alls in places where you are usually not allowed to do this. People have also used this to do generic programming, and here generic programming is used in the Haskell way, which means a program which does something depending on the shape of the data type. So it's not really, it can look at the shape of the data type and do something by depending on this shape. And there is a famous library called Scrap Your Boilerplate, and the main function has this form. This is a function which takes something of type A and leads to something of type B, and then it allows you to apply a transformation over the subvalues of this thing. So you can think of, you give it a list, and then gmap T knows by some black magic that it has to apply the first function over the elements of the list. And because these elements can have different types, you need to give a higher rank. It has to be a polymorphic function, so you can choose what are the elements. So it's also useful for generic programming. But even more, if you want to use lenses and you use the lens package, you're using this all the time without noticing it. Because a lens in the FunLab Hofen representation looks in this form. So that's also very similar to what Bartosz showed us today. But see, he used the profunctor representation. But the main thing is that I have, again, a for all F, functor F. So I have a for all in the top. So you can just look at the library. That's the first thing I found. So you have something called failing, which takes two traversals. And we don't really need to know what a traversal is. But the thing is, if you expand what traversal means, you will get for alls in the type. And it gets one traversal and another traversal and tries to apply the first, and it fails, applies the second. So you are using all these higher rank types all the time if you are using a bit more advanced optics in Haskell. And, well, I guess in Scala too. So this is my idea is that you show that this is really used in practice. It's really something you don't often face. You don't often write this kind of code. Yeah, luckily. I mean, if somebody has to write this kind of code for a job. I don't know if I envy or I think it's a curse, but anyway, that's several examples of higher runtimes in the wild. So, just go there and fly higher with functional programming.